For the third and final talk in this series of KIPAC in the World, we have Joe Liu. And Joe was a postdoc here at KIPAC from 2010 to 2014. He worked with Tom and Risa on modeling galaxy formation. He then went on to another postdoc position at Carnegie Institution for Science for a few years. And he has now been at Lam Research for approximately 7 years as a data scientist. And he's going to talk to us about human-machine collaboration for improving semiconductor process development. Thanks for coming, Joe.
Sure. Okay. Hello, everyone, and thank you for having me. It's my pleasure to be here again, and it's always good to come back and see old friends and new friends. Today, I'm going to bring a topic that can be new to you, but I think for people who know me, can certainly see the thoughts I put into this piece of work. Can trace back to my research in astrophysics. And for people who don't know me, hopefully what I'm going to present today are relatable to what you are currently doing or maybe what you are going to do in the future. This is a piece of work we recently published in Nature as a research article. And the title is, here I read it, Human-Machine Collaboration for Improving Semiconductor Process Development. And obviously, this is a teamwork. And I was lucky enough to participate in this research and contributed to leading the algorithm design. A little bit about the background of where I am. I'm a part of Lam Research. I'm not sure whether you know this company, but let me introduce you. I think it should be quite accessible to you. Everyone now has a phone, and I see a lot of people have a computer in front of you. All this electronics, even computer centers, data centers, GPU, CPU, they are all powered by computer chips. And in those computer chips, there are thousands, even millions of transistors in them. So someone needs to make them for you. And the people who are making them for you need equipment. So Lam Research is a wafer fabrication equipment provider and equipment and service provider. So we are building sophisticated equipments to build computer chips. And there are also a larger population in the company who bear PhD in physics and chemistry, working very hard to design those machines and also what we call recipe to build those computer chips. It's fair to say, pretty safe to say, every computer chip, especially the advanced one, have ever gone through Lam equipment at least once. We actually provide a very broad equipment coverage, from etching using plasma to etch a silicon wafer and build those small structures on wafer, and also deposit different materials on the silicon wafer so that you can do further etch, and also to clean the wafer and all out sort of services and support. We are a leading equipment provider in semiconductor sector, established 40 years ago, and we do global research and development, engineering, manufacturing, customer support, and the supply chain. And dated the end of last year, we are 19,000. We have 19,000 employees, and being $19 billion revenue company. More specifically, I work as a part of what we call Semiverse Solutions. This is a business unit within office of OCTO. And what we do is to enable infrastructure for data analysis, enable data science and analytics, machine learning, artificial intelligence, and also to build sophisticated simulation tools to create a virtual world for computer chip fabrication. A little bit about the history, because I think this context is important. So I think human society has been experiencing this exponential acceleration of capability and power. So probably around the middle of last century, I think a lot of innovations are really powered by computer chips or transistors. And there is a famous law, Gordon Moore, who was the founder of Intel, passed away earlier this year. Back in 1960s, point out there is a relationship between the size of the transistor on computer chip and the time. What essentially the statement was, the size of the transistor decreases exponentially as a function of time. The reason behind this scaling law is complicated, and this talk is not going to talk about it. However, from the standpoint of semiconductor equipment provider, we will say the reason behind this law is to a certain extent self-fulfilling prophecy, in the sense Lam Research and our competitors working collaboratively and competitively to make it happen. So the way we make it happen is to make our equipment more and more sophisticated so that we can enable different complicated processes to build wafers, computer chips with smaller and smaller sizes. When the tolerance becomes more and more stringent, you need to make sure your equipment can operate so precisely so that you can make nanometer scale structures on wafers. And every feature on the wafer has to be almost identical. So in order to make it happen, as we make the equipment more and more sophisticated, actually the equipment actually needs a lot of knobs, right? You have a whole lot of controls to conduct those processes. And the number of viable combinations of the processes that can result in observable difference on wafer increases as function of time exponentially. So we adopt this as Lam's law. So this is basically a consequence or the underneath driving force of Moore's law. However, this law also implies a problem. We call this a Lam's law problem. And this problem is not only for Lam, actually is a problem for the entire industry in the semiconductor to build computer chips. That is illustrated here, right? So customers usually ask for spec, right? So those big, semiconductor companies, they need to create certain transistors on wafer. So then they would specify what they want to build on a wafer. So then we need to come up with the equipment and also to make sure the recipe, which really means how to operate the plasma and how to introduce the chemistry so that the reaction in the chamber can happen in the way such that we can build those features, very, very small features on wafer. So that involves making hypotheses, prepare the experiment, choose different recipes, and then run those experiments, and also to do measurement on wafer, collect the images, and also do the analysis to find the viable solution that can deliver the process that can satisfy customers' spec. On the right-hand side is an example of a 3D NAND cross-section. of those chips. So this is our, I would say, smallest man-made structure in the world. And in particular, the aspect ratio is very, very high. It's even higher than the building actually man ever made on the surface of the Earth. So you can see all those structures, not only, you have to satisfy those geometrical specs, but also those structures need to be uniform across the entire wafer. The problem becomes a lot of tuning. So ironically, in this field, people are still tuning their processes with a trial and error way. So essentially, process engineers in semiconductor are still following what Thomas Edison did 100 years ago. Trial and error and figure out what can go wrong, what can help. This becomes a finding a needle in the haystack problem. And also, another point is running those experiments are actually very expensive. Wafer has a cost, running the tool has a cost, cutting the wafer will induce a significant cost. And also those measurements are destructive in the sense when you have to destroy the sample in order to do measurements. When you try to figure out different aspects of the wafer, you have to think about how to do it. It's really complicated. Because of this high cost, not only those R&D becomes very, very slow and difficult, generating new way of solving problem is also difficult. So to conquer that problem, we actually build a simulation. In the simulation, we can actually simulate how process can happen. So then you can try just as a game, right? So if you have a spec from a customer you want to achieve, and this simulator simulates the plasma and the surface interaction between the plasma and the wafer. So with input recipe, you can predict what's going to happen on the wafer to give you a certain structure. So by dialing those recipe parameters, you can see what's going to happen. And when you find a recipe that can satisfy this spec, you probably are happy with that recipe. So using this virtual test bed, we can actually try different solutions. And also we can try different solution approaches. Machine learning is one of them. So with that, we actually did a lot of simulations, not only with computer machine learning algorithm, but also with human. We invited process engineers with different level of experience. Some of them are senior engineers. They have been in this industry for more than 10 years. They have a very good gut feeling about what can happen if you dial in the process in different ways. Some process engineers are fairly junior. They just got into this company and had a very basic training. Here, what I'm showing is this is what we call progress tracker. That is telling you how far you are away from a customer spec target. What we see is this is actually quite satisfying in the sense we see LAMS process engineers are quite skillful in terms of getting the recipe close enough to the target very, very rapidly, right? However, we see after they make a significant progress with about 20 or 30 experiments, they start to struggle. And they have to struggle for a long time before they can nail down the process. And the best process engineer in this game actually costed $105,000 virtual dollars to solve that virtual problem. We also ask other people to try this game, even people with basically no experience in this particular field. One of our HR personnel actually participated in this. the characteristic shape of this progress tracker is, you can see it's all over the place, but they are just so persistent, and they can, they play the game for quite a few weeks. And what discouraging, however, is when we try machine learning model, right? And the machine learning model starting from knowing nothing about this phenomena, and is not satisfying either. Looking at the characteristic shape of this tuning, we find there is a rough tuning regime where human can make a very rapid progress, and a fine tuning regime where people make very, very slow progress, right? Human is very good in doing rough tuning because there are certain knowledge in there, and they can rapidly use their knowledge to navigate the parameter space to make a better recipe. But in fine tuning space, they start to find that their training start to lose the aid. They don't know what to do. So then we came up with a set of artificial intelligence solution to this. And the idea behind it is using Bayes' theorem. What's fascinating about this theorem is if you consider the way you describe a phenomena is using a set of parameters theta. And because you don't know about this system very well, essentially your theory is uncertain. So it makes sense to describe your theory probabilistically. So therefore, your theory should really be written as a probability distribution of theta. And what's nice about this theorem is you can always update your theory by taking data. When you have additional data, you can improve your theory to get your posterior distribution of your theory. When you do that, this is significant because when you build a model, right, and use the model to describe what can happen, you can use the data to make an improvement. And when you make an improvement, you can make a prediction. And what is additionally important is you can figure out, using the model predictive distribution, you can figure out where you are likely to make a further progress. For example, here you want to maximize this function, but at this moment you have only 4 observations. So your theory actually gives you a distribution of models. And the best point is at this value around 2, right? So with the posterior predictive distribution, you can now figure out where you're likely to be better than your current process. So you can figure out at -1, there is a chance you can be better than the current best, but the chance is pretty small. But if you are at 2 point something, the chance is significantly higher. And when you do that, you can actually, this gives you a framework to quantify what we call acquisition function. So you can go to the location of the parameter space to do your next experiment, because that's the experiment that you want to do. You can more likely to make a progress. So this is a very nice scheme to actually design new experiment for research and development. And when we did this on this virtual environment, we find the machine can rapidly find a solution. If we start early, even we start early, if we start slightly later, to use human-generated data to form a more robust prior for the AI can actually solve the problem even more rapidly. Putting things together, so you will see cost to target. The gray bar on the top is the best human benchmark. And when you use this Bayesian optimization motivated artificial intelligence agent to motivate your next experiment, you can have a significant cost saving. If you start to do handoff from human to machine slightly later, you still gain cost saving, but maybe not as much as some optimal point. Okay, conclusion. Research and development problem in semiconductor often are little data problem, and it really requires maximum leveraging of information in real experiments. Models don't need to be accurate, but they need to be useful and realistic. Human engineers continue to be essential for process development. This is what we see. And the rest of the company is very happy because they are not losing job taken by AI. And human first computer labs, this paradigm we demonstrated in the paper can significantly alleviate some of the tedious aspect of process engineering job. To close, I would like to acknowledge my collaborators, and this is truly amazing teamwork. And especially I want to point out of this, this is nine colleagues, four of them actually had a PhD in physics, and the three of them actually did astrophysics project in their PhD. Yeah.
Thank you, Joe. So questions? Risa.
This is really interesting, this human learning curve on this process, you know, the fast and then slow. How specific do you think that is to this chip design versus more generic to other things?
Yeah, we believe this is generalizable, especially when human deals with a complex system, right? A lot of professional training and advanced training really build the foundation of understanding of those systems, and they can make very rough understanding at the beginning using the education they gained back. But as soon as you go to very specific problem where the tolerance becomes very stringent, human may lose the advantage.
If I can ask a question, maybe you can't answer this, but are you also working on how you would remove the human earlier in the process, like train the machine learning better on the human experience?
Okay, yeah, this is astrophysical community, I guess. Yeah, this can be an interesting direction for me to go. Actually, I put in a lot of thought into it, but I wouldn't say that to my colleague.
Right. Okay. Great. And actually, could you back up to the slides? It went back very fast. That showed the performance at the end. Actually, the one before that, just in terms of interpreting it. But I think it was the slide on the right. So okay, so the white curves on the right are the humans, and then the
white is a human benchmark, the best process engineer involved in the game, and the blue are machine.
Okay, great. Yeah, and so you see how the machine just like kind of moves around a lot and then very rapidly goes to the solution.
Yeah,
right?
That's the nature of the algorithm, and also that's the nature of the problem, because the system itself is very complicated. It's actually very difficult to gain perfect understanding of the system. So you always solving the problem involves some probabilistic nature of part of the approach. So in Bayesian optimization, actually, if you write down the mathematics, you will notice there are two terms that determines your best shot for the next experiment. One term actually is called the exploitation, that is using the power of your predictive power of the model. The other term is called the exploration, that really comes from the uncertainty of the model.
Mm-hmm. Got it. Okay. Tom.
Thanks so much, Joe. That's really cool. Like here, the solution, when the machine finds it, right? It managed to find a recipe that satisfies your customer. It may be very far from optimal, though. So in the sense that, okay, yeah, so you're not breaking Lamb's law at this point, right? And so I'm curious how you think about, the more dramatic step could be if you really brought it down to only 10 recipes rather than 1,000.
Yeah.
You know, how can your approach help in that direction?
Right. This is a great question. And philosophically, actually is deeper than that, because really what is optimal, right? So it's actually quite difficult to argue a lot of times. And also, I would emphasize this is really in a business context, right? Actually, this really comes back to a question Roger asked earlier, right? In industry, right? When people think, I think there is a mindset difference between academia and industry. In industry, people have to consider a lot of practical issues. Essentially, the best for us is better than our competitors.
Right. Thank you. Okay, any other questions? Yes, Steve.
A very naive question. I'm wondering, is there something distinctly different when we look at that progress curve between what the human beings are good at and what the machines are good at?
Yeah, so this can, from this learning, we actually try to convey here. In rough tuning, human usually have their experience. They know, okay, for this type of a process, they are etching some material. They should use some chemistry. They should, you know, dial in the plasma in a certain way. So they already usually have a baseline to start, right? So machine usually cannot do that because it's a totally new problem for the machine. But for human, because they have all those experience, maybe last week, he did something for another customer. This week is a new customer coming to him, and then, you know, the problem need to be addressed in a very similar way. So all those experience come into this. And also domain knowledge can help them to build a hypothesis. So they can immediately tell by using a few experiments, establish some simple hypotheses, and then they can go quickly to test those specific hypotheses. And quite likely those hypotheses can be proven true.
If I could follow up, is what a customer wants from customer to customer, is it very similar what they want? In which case it seems like it would be easier to train. Yeah.
Actually, at this point, I would say, you know, in semiconductor industry, there are just a few giants, right? They basically have a significant market share. And also there are a lot of knowledge sharing. Again, you know, collaboratively and competitively, right? So they can be very, very similar.
Okay, thank you. So let's thank Joe again. With that,